Beneath a landscape of steaming vents, vividly coloured hot springs, and ground that pulses almost imperceptibly over time, an unsettling question lingers. How does one of the most studied volcanic systems on Earth continue to resist clear explanation? Why does the heat beneath Yellowstone National Park behave in ways that challenge long-standing models of how volcanoes are supposed to work? And what does it mean when the very framework scientists rely on to understand Earth's interior begins to fracture under the weight of new data? For decades, the system beneath the Yellowstone caldera was treated as the textbook example of a mantle hotspot, a relatively fixed column of hot material rising from deep within the Earth, feeding volcanic activity at the surface. This concept, often illustrated as a vertical plume punching upward through the crust, helped explain volcanic chains like Hawaii and was long assumed to apply cleanly to Yellowstone. Yet the deeper researchers probe, the less this system resembles that tidy model. Instead of a simple, vertically aligned heat source, the structure beneath Yellowstone appears fragmented, tilted, and dynamically interacting with the surrounding crust in ways that complicate nearly every assumption once held about hotspot volcanism. The historical record alone demands attention. Over roughly 2 million years, Yellowstone has produced several eruptions of extraordinary magnitude, events capable of reshaping vast portions of the North American landscape. These were not ordinary volcanic outbursts, but super eruptions, ejecting material across thousands of kilometers, blanketing regions in ash and altering ecosystems on a continental scale. Such eruptions require immense volumes of magma, yet the mechanism by which that magma accumulates, evolves and eventually mobilizes beneath Yellowstone remains far from straightforward. Traditional models suggest a large, coherent magma chamber gradually filling until pressure forces an eruption. What has emerged from modern imaging, however, is a far more complex arrangement. Seismic tomography, a technique that uses earthquake waves to map structures beneath the surface, reveals a multi-layered system rather than a single reservoir. Deep below, at depths approaching roughly 40 to 50 miles, or about 65 to 80 kilometers, there exists a broad region of partially molten rock. Above that, closer to the surface at depths of approximately 3 to 10 miles, or 5 to 15 kilometers, lies another zone, where melt accumulates in a more fragmented, sponge-like network. These zones are not neatly stacked cylinders of magma, but irregular, shifting bodies with varying degrees of melt, interspersed with solid rock. The implication is profound. Yellowstone's magma system is not a simple storage tank, but a dynamic, evolving network. Even more puzzling is the geometry of the supposed plume feeding this system. Rather than rising vertically like a straight column, evidence suggests it may be angled, perhaps even deflected by the movement of tectonic plates or variations in the mantle's composition. This challenges the foundational idea of hotspots as fixed, vertically oriented features. If Yellowstone's heat source is tilted or segmented, then the assumption that hotspots remain stationary relative to Earth's interior becomes less certain. The track of volcanic activity across the Snake River Plain, long interpreted as the North American plate moving over a fixed hotspot, may instead reflect a more complicated interaction between deep mantle processes and lithospheric dynamics. At the surface, the signs of unrest are subtle but persistent. Earthquakes occur frequently in the region, often clustering in swarms rather than isolated events. These swarms typically consist of small tremors, yet their patterns offer clues about the movement of fluids and magma below. Unlike tectonic earthquakes, which result from the sudden release of stress along faults, these swarms often indicate the shifting of pressurized fluids through fractures in the crust. The frequency and distribution of these events suggest an active system, continuously adjusting and redistributing energy. Ground deformation adds another layer of complexity. High-precision GPS measurements and satellite-based radar reveal that parts of the caldera rise and fall over time, sometimes by several inches or a few centimeters over the course of months to years. These changes are not uniform. Different regions of the caldera may uplift while others subside. Such patterns imply localized changes in pressure beneath the surface, likely tied to the movement of magma or hydrothermal fluids. Yet the absence of a consistent, predictable pattern makes it difficult to interpret these signals within the framework of traditional volcanic behavior. The hydrothermal system at Yellowstone further complicates the picture. Thousands of geysers, hot springs and fumaroles dot the landscape, driven by heat escaping from below. These features are not static. They evolve, shift, and sometimes appear or disappear entirely. Changes in water temperature, chemistry, and flow rates are routinely observed, indicating an intricate connection between the deep magma system and surface water circulation. This constant interaction between heat and water creates a feedback loop that can alter pressure conditions underground, influencing both seismic activity and ground deformation. One of the most challenging aspects of Yellowstone's behavior is the uncertainty surrounding how magma is stored and mobilized. In many volcanic systems, magma accumulates in relatively well-defined chambers where it can be monitored and modeled with some degree of confidence. At Yellowstone, however, the distribution of melt appears diffuse, with pockets of magma present within a largely solid framework. This means that the total volume of molten material may be significant, but it is not necessarily organized in a way that would easily lead to an eruption. Instead, the system may require specific conditions, such as the connection of multiple melt zones or the injection of new magma from below, to reach a critical state. Adding to this uncertainty is the role of the surrounding tectonic environment. Yellowstone lies within a region influenced by the stretching of the Earth's crust, known as the Basin and Range Province. This extension creates fractures and pathways that can facilitate the movement of magma and fluids. At the same time, it introduces additional variables that complicate the interpretation of geological data. Rather than being an isolated hotspot, Yellowstone may be interacting with broader tectonic processes, blurring the line between plume-driven volcanism and crustal dynamics. Recent findings have intensified the debate over whether Yellowstone fits the classic definition of a hotspot at all. Some evidence points to the possibility that the heat source originates not from a deep mantle plume, but from processes occurring at shallower depths, such as the recycling of oceanic crust or localized mantle convection. If this is the case, then Yellowstone represents not just an anomaly, but a fundamental challenge to the way volcanic systems are classified. The distinction between hotspot and tectonically influenced volcanism becomes less clear, raising questions about how many other systems around the world might also defy categorization. The implications extend beyond academic theory. Understanding the structure and behavior of Yellowstone's magma system is critical for assessing potential hazards. While there is no indication of an imminent large-scale eruption, the system remains active, and its complexity makes precise forecasting difficult. The presence of multiple melt zones, coupled with ongoing hydrothermal activity and frequent seismic swarms, suggests a system that is continuously evolving. This state of constant change means that models based on static assumptions may be insufficient to capture the full range of possible behaviors. Monitoring efforts at Yellowstone are among the most advanced in the world, employing a network of seismometers, GPS stations, and satellite observations to track changes in real time. These tools provide an unprecedented level of detail, yet they also reveal just how much remains unknown. Each new dataset adds layers of nuance, often complicating rather than simplifying the overall picture. Patterns that once seemed clear become ambiguous when viewed over longer timescales or in conjunction with other variables. One of the most striking aspects of Yellowstone's defiance of conventional models is the way its different systems interact. The deep mantle processes, the crustal magma network, the hydrothermal circulation, and the tectonic setting are all interconnected. Changes in one component can cascade through the others, producing effects that are difficult to predict. This interconnectedness challenges the traditional approach of studying volcanic systems in isolation, suggesting that a more holistic framework is needed. Far below Yellowstone National Park, the real story is not just a reservoir of magma sitting quietly under the surface, but a rising column of heat that refuses to behave like the classic mantle plume model suggests. Understanding why this system remains so difficult to predict requires shifting focus into the mantle itself, where temperature, pressure, and the physical properties of rock interact in complex ways that cannot be observed directly, only reconstructed through seismic signals and other indirect measurements. In classical geophysics, a mantle plume is described as a buoyant upwelling of anomalously hot rock rising from deep within the earth, potentially from near the boundary between the core and the mantle. This material is not liquid magma in the conventional sense, but solid rock that flows slowly over geological timescales. As it rises, pressure decreases, allowing partial melting to occur. That melt then feeds volcanic systems at the surface. The expectation in this model is relatively straightforward. A vertically oriented, stable upwelling that supplies heat in a focused manner, producing a chain of volcanoes as a tectonic plate moves over it. What is being observed beneath the Yellowstone caldera diverges from this simplified geometry. Instead of a narrow, column-like plume, seismic imaging suggests a broader region of hot material that expands laterally as it ascends. This spreading behavior alters the physics of the system. A narrow plume concentrates heat, increasing melt production in a localized zone. A broad upwelling disperses that heat, reducing the efficiency of melt generation in any single location while increasing the overall area influenced by elevated temperatures. This distinction is crucial because it changes how magma accumulates. In a focused plume, melt tends to collect into larger, more coherent bodies. In a diffuse upwelling like Yellowstone's, melt forms in scattered pockets distributed across multiple depths. These pockets may remain partially molten, interconnected through porous pathways rather than unified into a single chamber. From a mechanical standpoint, this resembles a permeable network rather than a pressurized tank. Pressure can be redistributed through the system instead of building uniformly, which is one reason large, abrupt transitions are difficult to anticipate. Another departure from classical plume theory involves the orientation of the upwelling. Evidence indicates that the hot material beneath Yellowstone may not be rising vertically, but is instead tilted, possibly by several tens of degrees. This tilt can occur due to large-scale flow within the mantle, or because of the motion of the overlying North American plate, which exerts shear forces on the ascending material. When a plume is tilted, the pathway from deep mantle to surface becomes elongated and complex, increasing the distance over which heat and melt must travel. A longer, angled path introduces more opportunities for interaction with surrounding rock. Heat can be lost, melt can stall and crystallize, and chemical reactions can modify the composition of the material. This creates a system where magma reaching shallow depths is not a direct product of a single source, but the result of multiple stages of transformation. Such a process inherently introduces variability, making the system less predictable than one fed by a direct, uninterrupted plume. The unpredictability is further amplified by the rheology of mantle materials. The mantle is not uniform. It contains variations in composition, grain size and temperature that affect how it flows. As hot material rises beneath Yellowstone, it encounters regions of differing viscosity. Some zones allow easier flow, while others resist movement, causing the upwelling to split, divert, or slow down. These variations can produce branching structures within the plume, effectively creating multiple conduits that feed different parts of the crust at different times. This branching behavior has direct consequences for volcanic activity. Instead of a single centralized supply of magma, Yellowstone may receive pulses of melt from different segments of the upwelling. These pulses can arrive asynchronously, interacting with existing melt zones in complex ways. Sometimes they may merge, increasing the volume of molten material in a localized area. Other times they may dissipate without significant effect. This intermittent supply pattern contrasts sharply with the steady-state assumptions often used in volcanic modeling. When compared to volcanoes driven primarily by plate tectonics, the differences become even more pronounced. At subduction zones, for example, magma generation is largely controlled by the descent of an oceanic plate beneath another plate. Water and volatiles released from the subducting slab lower the melting point of the overlying mantle, producing magma in a relatively predictable zone above the slab. The geometry is constrained, the source of melt is clear, and the pathways to the surface are often well defined along volcanic arcs. Similarly, at mid-ocean ridges, magma forms because of decompression melting as plates move apart. The process is continuous and broadly uniform along the ridge, producing basaltic lava that erupts in a relatively consistent manner. These tectonic settings provide boundary conditions that limit variability, making their behavior more predictable within certain parameters. Yellowstone does not benefit from such constraints. It is located within the interior of the North American plate, far from plate boundaries, meaning its heat source operates largely independent of the mechanisms that drive most volcanism. Without the regulating influence of subduction or spreading, the system is free to evolve according to the internal dynamics of the mantle and crust. This independence contributes to its complexity, as there are fewer external controls to stabilize its behavior. The interaction between the hotspot and the overlying plate introduces another layer of complexity. As the North American plate moves southwestward at a rate of a few centimeters per year, it effectively drags the upper portion of the system with it. This motion can shear the upper part of the plume, stretching and distorting it. Over time, this process may contribute to the development of the broad, tilted structure observed today. At the same time, the heat supplied by the hotspot weakens the base of the crust and the uppermost mantle, reducing their mechanical strength. This weakening can influence regional tectonics by making the crust more susceptible to deformation. In the surrounding basin and range region, where the crust is already undergoing extension, the additional heat may enhance the tendency for the land to stretch and fracture. This creates additional pathways for magma and fluids, further complicating the overall system. There is also evidence that the plume may interact with pre-existing structures in the mantle, such as ancient subducted slabs or regions of varying composition. These interactions can alter the trajectory of the upwelling, redirecting heat and material in unexpected ways. If the plume encounters a dense, colder region, it may spread laterally beneath it, creating a reservoir of hot material that feeds the crust indirectly rather than through a direct vertical connection. Such scenarios help explain why Yellowstone does not exhibit the clear, linear volcanic chains seen in other hotspot systems. The track across the Snake River Plain shows variation in eruption style, volume, and spacing, suggesting that the underlying process has not been constant over time. Instead, it appears to reflect a system that evolves as it interacts with changing conditions in both the mantle and the crust. From a predictive standpoint, this complexity presents a fundamental challenge. Forecasting volcanic behavior relies on identifying patterns and understanding the processes that produce them. At Yellowstone, the number of interacting variables, tilted upwelling, distributed melt zones, hydrothermal circulation, and tectonic influences, creates a system where patterns may be transient or overlapping. Signals that might indicate increasing activity in one context could represent normal fluctuations in another. Even the relationship between magma movement and surface activity is not straightforward. In many volcanic systems, the ascent of magma produces clear signs such as increasing seismicity, ground uplift, and gas emissions. At Yellowstone, these signals can occur without leading to eruption, as the system often accommodates changes internally. Melt can migrate laterally, pressure can be relieved through hydrothermal processes, and fractures can open or close in response to shifting stresses. This capacity for internal adjustment reduces the likelihood of sudden, large-scale failure, but increases the difficulty of determining when the system might transition to a different state. It is not that Yellowstone is constantly on the verge of eruption, but rather that its behavior does not follow a simple progression toward or away from such an event. Instead, it operates within a spectrum of activity where changes are continuous but not necessarily cumulative. The broader implication is that Yellowstone represents a type of volcanic system that sits at the intersection of plume dynamics and tectonic processes. It is not purely one or the other, but a hybrid shaped by both. This hybrid nature is what allows it to defy conventional classifications and why it remains a focal point for refining models of how the Earth's interior functions. As measurements continue to improve and data sets expand, the picture becomes clearer in detail but more complex in interpretation. The hotspot beneath Yellowstone is not a fixed feature delivering heat in a predictable manner. It is a dynamic system influenced by flow in the mantle, motion of the plate, and feedbacks within the crust. Each of these components evolves over time, ensuring that the system as a whole remains in flux. Understanding this interplay is key to grasping why Yellowstone challenges established volcanic science. It demonstrates that mantle plumes can deviate from idealized forms, that hotspots can interact with tectonic settings in significant ways, and that volcanic systems can distribute energy through networks rather than singular structures. These insights do not simplify the system. They expand its dimensions, revealing a level of complexity that demands new approaches to both observation and interpretation.